warm-up question told you to sit as still as possible and then turn and look at your neighbor and answer this question. How fast are they moving right now? Would anybody like to share what they said for the warm-up? How fast is your neighbor moving? I heard like whispers, but I can't hear what y'all are saying back there. Is that to call on people? All right, we can do that. Okay. Andy.
I would say they were moving a little bit slower than most people I know.
A little slower than most people you know. Oh, that's probably true. Okay. Anybody have a different answer they want to share? No? Not voluntarily? Sanjay? What'd you say?
I was saying they move pretty fast.
Okay, they're moving fast. What do you mean? How fast?
I'm not sure exactly.
Why do you think they're moving fast?
Because they moved closer to me in like a second.
Sorry?
They took like a second to move their head.
Oh, okay, because they moved their head. All right. Anybody have a different answer? Yes.
I think it depends on what you're comparing it to. So like compared to myself, they're not moving, but compared to the Earth's rotation, they're moving pretty fast.
Yeah, that's exactly where we're going with this. Paisley, right? Okay, good job, Paisley. She said it depends on what you're comparing it to, because compared to you, if they're sitting still, which is theoretically what they should be doing, they're not moving compared to you. But they are moving compared to some other things. If you're considering if they're moving with respect to the Earth's axis, then yeah, because the Earth is rotating. Okay, but you can also talk about it with respect to some other things. And we're going to get into that discussion today when we talk about motion. So that's actually part of our notes. Motion notes, we're going to start with that discussion of the warm-up. And then playlist 2, all these things are part of that, and that is what you can work on when we finish the notes. Although if it goes like last period, we won't have a ton of time. But your answer of the warm-up depends on your frame of reference. You're not moving compared to your neighbor. That's the answer I was expecting most of you to give me is 0. Okay? And if you said that, that's fine. You're not moving. However, you're moving at approximately 750 miles per hour to the east because that's how fast the Earth is rotating. So maybe you told me that. Maybe you Googled it. Okay, and technically, since you're on the Earth, you are also moving at that 750 miles per hour to the east. Or maybe you told me that you're moving at 66,000 miles per hour because that's how fast the Earth is moving around the sun as it is revolving along its orbital path. Or maybe you told me that you were moving at 483,000 miles per hour because the whole solar system is also orbiting around the center of the Milky Way galaxy. Or maybe you went even farther out than that and you told me that the whole galaxy is moving toward Andromeda at 1.3 million miles per hour. I don't know. Maybe you looked up some of that stuff. Maybe not. Okay, but your answer depends. There's not a right answer because it depends on your frame of reference and how you are describing your motion. And that's where our notes are going to start today. Frame of reference. We define our frame of reference by choosing a reference point and describing objects' change in position compared to this point. When you left home and drove to school today, you could say that you were moving with respect to your house. In this example, your initial position or your home would be your reference point, and maybe you would say something like, I drove 3.1 miles north to get to school, okay, or whatever. Okay, but you would be describing it with respect to your house as a reference point. Okay, often when you're talking just in everyday life, you are the reference point because you're describing things from your perspective. Okay, for example, you might say, he was running away from me, okay, or she came right at me. Okay, and those would be descriptions of the motion of the things around you with respect to your own position. Okay, and so a lot of times your frame of reference is just your perspective. But again, in physics, sometimes you're going to be asked to assume a certain frame of reference as you approach a question, or sometimes you need to assume a certain frame of reference in order to answer a question maybe more easily or maybe correctly or whatever it may be. Okay, but we can only describe motion with respect to a reference point. So you have to have a frame of reference, and it needs to be described and defined and identified. Okay, so for example, when compared to the buildings along the road, the girl in the passenger seat is moving. If you look at this girl right here, with respect to these buildings in this animation, she is moving. But if you compare her motion to that of the driver, she's not moving at all. And this is analogous to you're not moving compared to your neighbor, but you are compared to the sun type of thing. Okay, so it really depends on how you describe that frame of reference. As we talk about types of motion in this unit, we're going to discuss 3 different types of motion. Things being at rest, which means their position does not change. Things moving at a constant velocity, which means their position changes the same amount each second, or we can also state that as these objects have a uniform change in position. Or we can talk about objects undergoing acceleration, in which the position changes non-uniformly each second. And that just means that my position would get farther and farther and farther away, not in the same increment. Okay, non-uniform. Now for today in class, we're going to focus just on constant velocity for now. In fact, all of playlist 2 is things that are moving at constant velocity, or things that aren't moving, because technically that would be a constant velocity of 0. Okay, but we're not going to focus on acceleration until playlist 3. Okay, so for now you can kind of put that one out of your head for a little bit, but we're going to focus on things that are moving where their position changes the same amount each second, or where their position doesn't change at all. But we are eventually going to talk about all 3 types of motion. We can also talk about ways to represent this motion. And we're going to look at really just one of these today, and that is the dot diagram or motion map. But later on in some other notes, we're going to also look at data tables and graphs. Our graphs could be position time graphs, which are also called XT graphs, where X represents or is the variable for position and T is the variable for time. Velocity time graphs, where the V is the variable for velocity and T is time. And acceleration time graphs, where A is acceleration and T is time. For now, though, we're not going to focus on acceleration graphs at all. And we're really not talking about these graphs today, but we are going to look at dot diagrams as a way to represent motion. And then we're going to look at some numbers as a way to calculate that motion. But we do have many tools to represent motion of an object in physics. So dot diagrams are motion maps, data tables, and graphs. And again, we're going to get more into these later on. All right, so let's talk about the dot diagrams first. Okay, dot diagrams or motion maps. These are going to be representations of motion that use dots to mark the position of an object for set intervals of time. The time interval is assumed to be 1 second unless otherwise stated. So if you look at the dots on my screen, you would assume that each of these dots is left at 1 second intervals. So we have a dot, and then another second we have a dot, and then another second we have a dot, and then another second we have a dot. Now the thing is, I don't know which way to read this, because it could be read from right to left or from left to right. So typically the direction is indicated using arrows or by marking the reference point with a 0. So if you see this added, now I know that it's telling me to start here and to read them from right to left. Or instead of an arrow, you could see a 0 marked to show, hey, here is my initial position, 0. Okay, or initial time, here's my position at time 0. So if you see that 0 or if you see an arrow, then it's going to tell you where to start reading. But again, dot diagrams use dots to mark positions of an object for set intervals of time, and specifically that's going to be each second unless it states otherwise. A lot of times these dot diagrams will also include a grid like this, a number line or a grid of some kind that allows you to see how far apart they are. Of course, if you're using a tool in a lab, you might have to physically measure how far apart those dots are. But the spacing between the dots shows how far an object travels in 1 second. This means we can find an object's instantaneous velocity, and that should be a term that you know from your definitions tasks, but instantaneous velocity is the velocity at that instant, at that moment. How fast is it right now? Okay, and so if you look at this example, you can see that each second this object is moving 2 meters to the left, or negative 2 meters each second. And so I can tell that if I'm moving 2 meters each second, that I'm moving 2 meters per second in that negative direction. So I can tell the instantaneous velocity at any point there. You can also measure the spacing between the dots, again, if the number line's not provided, but oftentimes it is represented on a number line or on a numbered grid so that you can just read the markings. Okay, so you can see when it's moving easy enough because the dots are going to be spaced apart as the object is moving and leaves a dot at the next position. However, if it stops, because what a dot diagram is really kind of mimicking is something called a ticker tape, which is a tool that we sometimes use in lab that physically makes a dot each second or each whatever interval you set it at. And you can measure the distance apart. But if that object stops with a ticker tape, you're going to get a blob of a bunch of dots that are all overlapping because it keeps hitting that spot in the same place because it's not going anywhere. Okay, and this is really hard to read. Because an object stops, you could see this, but those overlapping dots, I can't tell how many seconds that stopped. So if we're actually drawing one by hand instead, this is what we do. You're going to show stacked dots at the same position for each second that the object stopped there. So now I know this object started here, okay, and then after 1 second, and then another, and then another, and then another, and then it stopped and it's still at the same position for these next 4 seconds. Many dot diagrams will add arrows between the dots to better illustrate the object's motion. So again, now I'm kind of combining the different things we talked about. I can see to start here, I can see I'm moving to the right, to the next dot. That's 1 second, here's 2 seconds, and then 3, and then 4, and then I stopped for 5 and 6, and then keep going, okay, moving forward. But I can see the direction, and the arrows, when you see them, represent that instantaneous velocity. The longer that arrow is, the faster the object is moving at that instant, because it's traveling a greater distance in that second. If it travels farther per second, it's traveling faster. Okay, so again, when you see this, longer arrows mean you're moving faster, shorter arrows mean you're moving slower. All right, so that's the motion map or dot diagram. Now I'm going to talk about how we can calculate velocity. Dot diagrams, by the way, are only one of the representations. We're going to look at the other ones later on, but first let's do some math. Okay, so whenever we approach any sort of calculation problem, and guys, if you haven't been writing anything down, I need you to write this one down because this is going to be quite a bit of math. And I mentioned yesterday that whenever we approach math problems in this class, that sometimes we just get to pull an equation from here, but sometimes it's not set up to solve what we need to, so sometimes we have to rearrange it and manipulate our equation. And other times we have to derive new equations. And I told you yesterday that in this course, oftentimes, instead of even asking for a number answer, they will ask you to simply derive the equation in terms of variables. And that's what I'm about to do with you in a moment after I go over these rules. We'll plug the numbers in at the end. But you need to know how to derive an equation. So this is going to be a lot of algebra, okay? Just a warning beforehand. So hopefully you love algebra, okay? If not, you're going to either have to love algebra or you're going to have a love-hate relationship with AP Physics 1. So whenever we approach a problem in this course, and in this case we're going to calculate velocity, the first step that we're going to do in our calculation is to define and label a positive direction. Maybe the question does it for you, maybe it doesn't. Okay, if it doesn't, you have to do it. So you can choose whatever you want, but by convention, we usually assume the same thing that we would in math, like on a coordinate grid. Typically, up along your y-axis is positive, down along your y-axis is negative. Typically, to the right along your x-axis is positive, to the left along your x-axis is negative. So that's the convention we use, but you don't have to. If you want, you can define down as positive. It doesn't matter as long as you label it. Okay, so choose what you want. This is the convention that I typically use. Use a grid or sentence to label that positive direction. That's step 1. Step 2, indicate in words what portion of the motion you're considering. Okay, so if we're looking at a scenario where we have, multiple objects, are we looking at just one of them or are we looking at all of them? Okay, or if we have an object that is moving both forward and down, am I looking at just the horizontal motion or just the vertical motion or both of them? Okay, and so you need to indicate what you are considering or what you're trying to solve for in that question. Okay, so that's step 2. So step 1, label your positive direction. We'll define it and then label it. Step 2, indicate what portion of the motion you're considering. Step 3, fill out a chart of these 6 kinematic variables Include direction in units so you can see any discrepancies before you do the math. And these are the variables it's talking about because these are the variables that show up in the equations that you have on your AP Physics 1 formula chart. And when I say kinematic equations, they're the first three. Okay, and these are the variables. V naught is initial velocity. V is final velocity. A is acceleration, T is time, X naught is initial position, X is final position. Now for today, we're going to be talking about objects moving at a constant speed. So for today, keep this in mind as well. We're not going to have any acceleration. Acceleration is going to be 0, which means that my initial velocity is the same as my final velocity because it's not changing. I'm not speeding up, I'm not slowing down, I'm not stopping. Okay, it's going to be the same the whole time. Also, if it's undefined, it's easy to assume your initial position to be 0. If I say, how far away did you go, or how far away are you, and you want to be like, well, I'm, 12 meters away from where I started, or you could be like, well, I'm 12 meters away from this other person, but it's easiest to define your initial position as 0. All right, if it's not defined for you. So these are your variables. So that's your next step, is to make a chart and start labeling what you know. And then your next step after you've labeled those is to choose the kinematic equation or equations that you need to use to find your answer. And that's going to be based on the variables you have, because you're going to have to start looking at, what do I know? Okay, what can I find? How can I use that to find what I need? Sometimes it's just one step, but usually it's more than one. The first three equations are the same ones on your AP Physics 1 formula chart. The fourth equation is not on here. It's actually the equation I showed you yesterday. Average velocity is displacement or change in position, x minus x naught over time. This equation can be derived from the second one. I'm not going to get into that right now, but this is an equation that's not on your sheet. It's one you should know, though, and you're welcome to write it down in your notes. But the first three are on this formula chart. Do you have a question? Okay. All right, so now that you have chosen an equation, okay, let's go ahead and work through an example problem. If I were you, I would copy this problem down. You're going to love it. Get ready. All right, it says you are walking to physics class at a speed of 0.50 meters per second with respect to the ground. Your friend leaves 2 seconds after you and walks 1.5 meters per second in the same direction. How far before your friend catches up with you? Okay, so we have the question. It seems easy enough. Okay, but we're going to go through the steps that I just showed you. Step 1 is to define the positive direction. It's easiest to be the direction I'm going to be positive, so that's what I'm going to do, is I'm going to say, well, I'm walking in the positive direction. So the direction I'm walking is going to be positive, so that means this 0.50 is going to be a positive 0.50. Okay, that's my positive direction. Step 2, what portion of the motion am I looking at? Well, I'm looking at what happens from when I left until my friend catches up. Okay, that's what I'm looking for. Just that motion from when I left until my friend catches up. I don't care what happened before or after that. I don't know anything about what happened before or after that in this particular scenario. I'm looking at both my motion and my friend's motion. And then the third step is to start labeling these variables. So I've already listed them out, and we're going to make a table for each. But I have variables for me and for my friend, because there's 2 people here. Okay, so if we start labeling these, okay, it says I am walking, and I already said I'm going to call this positive 0.5. So positive 0.5 meters per second is my initial velocity. There's nothing here about acceleration, so I'm going to say that my final velocity is the same. They're both positive 0.5 because my acceleration is 0. Okay, so for now, that's going to be the case for all of them. Your V naught and V will be the same, and acceleration will be 0 until we start talking about acceleration. Then, of course, that's not going to be the case. It doesn't tell me anything about my time, so I don't have anything to fill in there. Okay, but for my initial position, it doesn't tell me what my position is. It does tell me I'm moving with respect to the ground. Okay, so I have a frame of reference here. Okay, but my initial position isn't defined. But I'm going to go ahead and call it 0, because that's easy. If I'm looking for how far before my friend catches up with me, I mean, I could say, well, I'm going to start at 20. Why not? And then I'd have to find my answer and then subtract the 20 out. So why would I do that? Okay, if it's not defined for you, it's easy to assume your initial position is 0. And again, because the question says how far before your friend catches up with you, okay, I'm looking for my final position. And that final position will be my friend's final position as well, because we're looking at when we're in the same spot, when we catch up with each other. Okay, but let's go ahead and label the variables for my friend. My friend's velocity is 1.5 meters per second in the same direction, so it's also positive. If it had said opposite, I would need a negative sign. Okay, and again, their velocity is not changing either because they are also not accelerating. The time, if I look up here, it doesn't tell me a time that they're walking for, but it does tell me that they leave 2 seconds after I do, which means that they are going to be walking for 2 fewer seconds than I am because they started later. And so I know that I can write this in terms of my time. So if I walk for T1, whatever T1 is, they walk for a time of T1 minus 2. Okay, so far so good? All right. The other thing I've done is I went ahead and said the x's are going to be the same as me. So now that we have the variables labeled, we can take a look at our equations. And since everything here is constant velocity, that's what that fourth kinematic equation is for. Since there's no acceleration, let's use the constant velocity equation. That constant velocity equation states that the velocity, the average velocity, since they're the same, is equal to the change in position, or final position minus initial position, over time. Okay, this is the equation we had in our notes the other day. But I, again, have 2 different people here. I'm going to use this equation both for me and for my friend. And I'm going to call my velocity V1, and my friend is going to be V2. My time is T1, my friend is going to be T2. Okay, now our positions are the same, because there is no x1, x2, because we're going to end at the same spot. That's the whole point, when we meet. And we started at the same spot, because it didn't tell us otherwise. So I don't have to worry about 1's and 2's up here. So these are my 2 equations. Again, ultimately I'm trying to solve for x, and both equations have an x in them. Okay, but if I look at this from here, what could I do next? There's a couple of things I can see looking at this. Okay, first of all, I can see that I have, for T2, is equal to T1 minus 2. I see that I have this value that I could plug in here instead, so that I have 1 fewer variable on my screen. Okay, and I could do that here. I also see that the initial position for both is 0. Okay, and because the initial position for both is 0, this equation, x minus x naught, x minus 0 is just x. So I could get rid of the x naught in both of those. Okay, and so now I have 2 different equations. V1 equals x over T1, and V2, so my friend is V2, equals x over T1 minus 2. Questions so far? All right, so I'm going to make that a little cleaner looking in just a second. But looking at this, again, I'm trying to find x, and I'm looking right now because I don't have enough numbers to solve for x is the problem. I don't know what T1 is. Okay, I know what V1 and V2 are, but I can't solve for x if I don't also know T1. So I have 2 variables that I don't know in each of these equations. And the only way I can solve an equation when I have 2 different variables in it is to use a system of equations. Okay, and so these are the 2 variables they have in common, but I'm ultimately trying to find x, so I don't want to get rid of that. I don't want to substitute in for that. I want to substitute in for T1. So if I can get both of these equations equal to T1, I could then set them equal to each other, and then I could solve for x. And that's exactly what we're going to do. Okay, because we need x, that's what the question asked for. Instead of focusing on that, we're going to see if we can get both of these written in terms of T1. So we're going to solve both of our equations and set them both equal to T1. So let's start with this one first. If I want this to be equal to T1, I can't do that if it's in the denominator. So I'm going to multiply both sides of my equation by T1 to cancel it. And that leaves me with T1 times V1 equals x. Okay, now if I want to get it equal to T1, I can simply divide both sides by V1, and I have T1 equals x over V1. Okay, so that one was pretty painless. T1 equals x over V1. It's the other one that's not going to be quite as fun. Okay, so let's take a look at this one. This is what I had once I had crossed off my x naught. So I have v2 equals x over t1 minus 2. And again, I need to get this equal to t1 so that I can set the two equal to each other and solve for x. So let's go ahead and do that. So we're going to need to get, again, t1 out of the denominator, but it's also being subtracted down there. So I have to multiply the entire thing, t1 minus 2, on both sides. And then I get this, v2 times parentheses t1 minus 2 equals x. From here, I need to distribute that v2 into those parentheses, and that leaves me with this, v2 t1 minus 2 times v2 equals x. Again, still need to get t1 by itself, which means I need to move this minus 2v2, I can add 2v2 to both sides. So that leaves me with v2 t1 equals x plus 2 times v2. That's a little cleaner to rewrite it. And again, I need t1 by itself, so I'm going to divide both sides by v2. And now I have an equation equal to t1. t1 equals x plus 2v sub 2 divided by v sub 2. Again, I told you it's a lot of algebra, and we're not done yet, because we still have to set these equal to each other. We haven't actually solved for anything. All right, so put it up here. Now I have two equations, both equal to t1, that I can now set equal to each other. X over v1 equals x plus 2v2 over v2. If I have two fractions set equal to each other, what do? What's the easy step that they teach you in like junior high math? Silence. Cross multiply. That's what we're going to do. Okay, so we're going to cross multiply, and that's going to give me this. X times v2 equals v1 times x plus 2v2. And now I have a situation here where I need to distribute this into my parentheses, giving me this. Okay, so I have x v sub 2 equals x v1 plus 2 v sub 1 times v sub 2. Again, I told you it's a lot of algebra. And sometimes the questions don't give you any numbers at all, and they're going to ask you to do this and solve for an equation for whatever variable they ask for in terms of whatever other list of variables they give you. So you actually have to do this whole process without even ever getting a number. All right, but we're not done yet. So again, we're trying to solve for x. That's the whole point. What is x? So we need to get x on the same side, because I have two x's right now. So I'm going to go ahead and subtract x v1 from both sides so that I have both of my x's on the left. Okay, so now I have this. X times v2 minus x times v1 equals 2v1 v2. Anybody know how I can get the x out of this side? Isolate it algebraically. What's that called? These two things have a like term. What do? Factor it out. X times v2 minus v1 equals 2v1 v2. Again, I want x by itself. Now I have a way to get it by itself. I can divide both sides by v2 minus v1. And that's exactly what we're going to do. And that is where we get to substitute. But by the way, again, sometimes on the AP test, the FRQ section, you have a derivation question, and sometimes that's the answer. I mean, not that exactly, but this whole process, getting to that, would be the answer you write on your test. You don't even put a number in. That's why I'm having you rearrange it first. Now, could you have put numbers in first and then tried to do it and it would have looked a little easier? Yeah, you still would have had to do a system of equations though. All right, so let's go ahead and substitute in now that we've got this equation. That's my equation. Let's plug in. 2 times v1 was 0.5 because I'm v1, I'm number 1. My friend was number 2, so times 1.5 over v2, 1.5 minus v1, 0.5. And if you were to multiply this, divide by this, you're going to get 1.5 meters as your answer. So you and your friend would meet up after 1.5 meters based on the numbers in this question. All right, as I said, a lot of algebra. Okay, so it does take some practice. I know you guys aren't, well, I don't know. Maybe you're used to manipulating the equations with variables, but I know a lot of times in math they have you plug the numbers in first. Okay, which you can do in a question like this, but in the derivation ones, you have to be able to do this. So I would recommend you practicing doing it this way. You can do it both ways if you want to check it afterward in case you're worried about a mistake, at least in class. On the test, you got to get fast at this stuff because you only have a little bit of time for each question. Okay, so that's how you solve it whenever you have two objects that are moving with respect to the ground, and you assume in that case that they're both moving with respect to some zero stable position. But what if your reference point is moving? What if it's not the ground? What if I wanted you to answer how fast you appeared to be from your friend's point of view, or something like that? If your reference point is moving, then you have to start talking about how fast objects are moving with respect to each other. How fast do they appear to be moving to you? And so we need to have something called, or discuss something called relative velocity. I'm going to start with a video clip. I think this is from like the 1960s. There it is, 1960. I thought it was the 50s. Okay, on frame of reference. I'm just going to show you a couple minutes of the clip because it's like 27 minutes long. So we'll watch a couple minutes, but it's kind of cool, the demonstrations that they do.
We're used to seeing things from a particular point of view. That is, from a particular frame of reference. And things look different to us under different circumstances. At the moment, things look
You look peculiar. You're upside down.
No, you're the one that's upside down.
No, you're upside down.
No, I'm not. He's the one that's upside down, isn't he?
Well, let's toss for it.
All right.
So this toss for it.
Okay. You lose. He's the one that's really upside down. You better come into my frame of reference now.
Oh. My frame of reference was inverted from what it usually is. That view of things would be normal for me if I normally walked on my hands.
This represents a frame of reference. Just three rods stuck together
It's
so
your
that each
it's
is
your
at right
X, Y,
angles
and
to
Z
the other
axes.
two.
It's X, Y, Z axis.
Now,
That's all
I'm
it
going
is.
to move in this direction. You see the frame at the same spot on your screen, but you know I'm moving this way because you see the wall moving this way behind me. But how do you know that I'm not standing still and the wall moving? It was the wall that was moving. Now the wall has disappeared, and you have no way of telling whether I am moving or not. But now you know that I'm moving. The point of this is that all motion is relative. In both cases, I was moving relative to the wall, and the wall was moving relative to me.
All motion is relative, but we tend to think of one thing as being fixed and the other thing as being moving. We usually think of the earth as fixed, and walls are usually fixed to the earth. So perhaps you were surprised the first time when it was the wall that was moving and not Dr. Hume. A frame of reference fixed to the earth is the most common frame of reference in which to observe the motion of other things.
Sorry, the thing's buffering a lot, but I wasn't going to show you the whole thing anyway. So again, it's kind of weird whenever things are moving you don't expect to be, but you can describe the motion even whenever he was stationary and the wall was moving. The wall was still moving relative to him, okay, or he was still moving relative to the wall. So you can always describe motion relative to your reference point. In fact, you have to describe your motion relative to whatever your frame of reference is. But if your frame of reference is moving, then your velocity, how fast you're going, is going to appear different than what you think you're actually doing. Okay, relative velocity is the mathematical comparison of two or more objects' velocities. For example, How fast do the trees appear to move when you're sitting in a moving car? If you're driving down, 99 going 70 miles per hour, and you look out the window, the trees look like they're moving past you. Okay, and they look like they're going backwards. If you're going 70 miles per hour, the trees look like they're going 70 miles per hour backwards. Now, of course, we know they're not moving, and it's just us that is moving, but they appear to be moving relative to us. So they have relative velocity. Okay, how fast does your mom appear to move when you're sitting in the back seat of the car while she's driving? So the trees, you look out the window, and they look like they're going 70 miles per hour that way, but if you turn and look at your mom, she doesn't look like she's moving at all, because with respect to you, she's not. But with respect to the road or the trees, she is. Okay, so again, we have to talk about our velocity with respect to our frame of reference, and sometimes that reference frame is also in motion. So let's talk about some examples whenever you have both an object and an observer or a frame of reference that is moving. Okay, so when you are moving, and this is just a general rule if you want to jot it down, and you probably already know this because it's real world experience that everybody's had, but objects approaching you from the opposite direction appear faster than their actual ground speed. If you're driving down the road going one way and somebody's going the opposite direction, they look like they go really fast when they go past you, okay, because from your frame of reference, they appear faster than they're actually moving. Objects that are passing you going the same direction appear slower than their actual ground speed. If you're driving down the road and somebody pulls up beside you and is, trying to pass you, maybe they're going 5 miles per hour faster than you are. You look out the window, they look like they're moving 5 miles per hour with respect to you because they're going that much faster than you. But that is much slower than their actual speed if you're going 50 and they're going 55 or whatever. If you pass an object, that object appears to move backwards. This is like the trees on the roadway. When you look out the window, you pass them, they look like they're going backwards. But it's also true when you pass other moving objects like other cars. Think of yourself as being in this red car. As this red car passes these other cars around it, if you were to look out the window, they would look like they were going backwards from your perspective. Okay, kind of slowly backwards, I guess, depending on how fast you're driving, but they would look like they're moving backwards. Here's an equation you can use to calculate relative velocity. This is not on your AP Physics 1 formula chart, so it is something that you might want to write down. The equation is the relative velocity of the observed velocity is equal to the velocity of the object, whatever it is you're looking at, minus the velocity of the observer. Okay, so object minus observer. So let's look at an example. It says you're driving east at 50 miles per hour when a wrong way car comes at you 40 miles per hour to the west. How fast does the wrong way car appear to move from your frame of reference? So they just told you your frame of reference, meaning you're the observer, and you're looking at this object, in this case this other car. But it's a little trickier than just plugging those numbers in, because the other thing you have to consider is that velocity is a vector. So if you're moving 50 miles per hour east and that other car is moving 50 miles per hour west, you need to define one of those as the positive direction. One's positive and one's negative because they're opposite directions. Again, by convention, we're going to call east positive. So I'm going to say we're going positive 50 as the observer, and that object, that other car, is going negative 40. So that's what I'm going to plug in. The relative velocity would be equal to that negative 40 minus my positive 50, and negative 40 minus 50 is negative 90, which I could also write as 90 miles per hour west because I defined west as the negative direction. Okay, so again, this is how you can use that equation if you're asked to find relative velocity. All right, so for the rest of the class period today, which is not much time, you guys have about 5 minutes. 6 minutes. You have playlist 2 to look at, so maybe you need to pick something up if you didn't grab it. Maybe you have questions because you're already looking at it. But take at least a few minutes to look over this stuff and see if you have any questions about 110, 111, or 112, or 113. But all of this is due on the 12th, so you have plenty of time between now and then to get it finished.